All right, so last thing we're going to look at is 8.5 part 4, which is really a review of everything we did Monday, Tuesday, and Wednesday, Thursday, except we had one day off because of MCAS, but it's in 3D. So really, I could have put some 3D questions on the test, and I doubt most people would have had a problem with it. Because if you understand that 2D, 3D is really the same thing. Right? One thing we're going to kind of stay away from a little bit in 3D is sketching. The sketching is a lot harder to do in 3D, so we're going to stick with just more numbers. But if you kind of want to visualize what we've been doing and what we're going to do now, this is where we've been before. Okay? Think of that as like the bottom of a box. Okay, you're looking into the box. Well, the XY plane is where everything we've done so far is. The Z plane gives us now a 3D axis. I can't really say up, down, left, and right anymore for directions. We used to say X was left and right, Y is up and down. But now in 3D, it's a little different. So the way you can visualize the axes in 3D is if you use your right hand and you look at your index finger, middle finger, and thumb. They hold them like this. Your index finger points in the direction of the positive x-axis. Your middle finger would point in the direction of the positive y-axis. And your thumb would point in the direction of the positive z. If you use your left hand, then what happens is your thumbs point in opposite directions. All right, so right-handed. This is called a right-handed coordinate system. So if you think about it like on your desk in front of you, like the x-axis would be going like front and back towards you, like towards me and towards you. The y-axis would be towards the door and the windows. And the z-axis would be what's coming up off the desk. So x, y, z. So what we're pretty much going to do is I'm going to show you something we've done in 2D, and then I'm going to extend it to 3D. Right? Once you see how this first one works, you're going to kind of get a feel for how all the formulas are going to work today. So this is something we've done before. Okay, this is the distance formula. And this is just to kind of warm up getting used to 3D. Okay, this formula doesn't even have anything to do with a vector. This is just you've got a point, you've got another point, and you want to find the distance between them. So in 2D, that's how you do it. The x1, the x2, the y1, and the y2, those are your coordinates of your point. So, I'll something like this. Point 1 would be this, and point 2 would be this. And then you'd plug those 4 numbers in those 4 spots, and there's your distance. Now, in 3D, we're going to basically use that same formula. We're just going to add one more thing, one more calculation onto the end of it to make it 3D. And that calculation is going to follow the same pattern as the first 2 that you've got right there. So the difference in 3D is now P1 has an x, a y, and a z value, and P2 also has an x, a y, and a z. You can still call these coordinates, but you can't call it an ordered pair. An ordered pair is a coordinate that specifically has 2 numbers. This is called an ordered triple. It's a coordinate with 3 numbers. So, anybody have a guess how we're going to extend the 2D formula to make it 3D? I'm going to add like one more thing onto the end of that. Yep.
Plus z2 minus z1.
Is
and
plus
in parentheses.
In parentheses.
And then squared.
And then squared. Yeah. And that's how all the formulas work today. Basically, take what you did before and just do it one more time with the z's. So now it's the difference between the x's, squared, plus the difference between the y's, squared, and this is the new part. The difference between the z's, squared. Okay, and again, not even a vector problem. Just practicing doing something in 3D first. Alright, so here are two coordinates in 3D, and I want to find the distance between them. Just like I always suggest with a distance problem, put your square root, put that first. Trying to keep it on the board, but it's the best I can do. All right. How about Matt? Can you tell me for the x2 minus x1, what would I put in here using my numbers?
-1 minus 4.
You know what? Let's just make sure we keep it in. It's not critical, but we should try to just match that order.
4 minus -1.
Yeah. If we're going to match this minus this, do the second one minus the first one. So 4 minus -1. Perfect. And we square it. Abigail, can you tell me the next one?
3 minus 2, or 3 plus 2.
So same idea I mentioned to Matt. Just to keep it so if somebody looks at it, they can match it up with the formula we used.
Minus -2.
Say it again.
3 minus -2.
So that would be y1 minus y2.
-2 minus 3.
-2 minus 3.
Sorry.
Yeah, it's okay. So the order doesn't particularly matter here, but we're going to do some formulas where the order does matter. So just to get used to following the order, even when it's not important, we just, we should do that. So -2 minus 3, and we square it. And Jack, how about the last one?
5 minus 2.
Yeah, 5 minus 2. And we square it. All right, so we'll do that out and see what the distance is. Francesco, what's 4 minus -1? And then when you square it,
25.
okay, so we get 25. And Eli, -2 minus 3.
-5.
And when you square it,
25.
25 again. And Casey, 5 minus 2. And when you square 3, 9. So the distance between these 2 points is the square root of 59. Questions on finding the distance between those 2 points? All right, so now we're going to do the same idea, but we're going to get into the formulas that we did with vectors. Every formula we learned had an x and a y in it. All you have to do is copy the same pattern one more time for the z. Okay, well, let's try that. So what I'll always do is I'll put what we did in 2D before. If you want to write it down again, you can, but you already have this in your notes. So this is what we learned in 2D. We have 2 special unit vectors in 2D, I and j. Can't really say they point up, down, left, and right anymore. I'm going to say I points in the direction of the positive x-axis, and j points in the direction of the positive y-axis. I'm going to need one more special unit vector, and that's going to point in the positive direction for the z. Anyone have a guess what we're going to name that other special unit vector? Yep.
Plus CZ.
Um,
Or would it be Z?
no, we're not going to use z for the name of the unit vector.
Oh, I thought you were asking. Never mind.
We'll call the component z. Like this is the actual component on the x-axis. This is the component on the y-axis. And we'll use c as the component. But we need a letter to indicate that it's going up. Or it's going 3D. Yeah.
VK.
K. Yeah, we're going to use k.
He took my answer.
He took it?
Yep.
Oh, no.
Did you give him the answer?
Yep.
Okay. Yeah.
No.
So in 3D, think of like what we did before. Remember we had i's that were 1 unit right, j's were 1 unit up, and we stacked them together to build a vector. Well, k is just another vector that we could stack, and it allows us to build in 3D. So if I and j's move you forward and back on your desk, and left and right, k is a vector that lets you come up off your desk to build something in 3D. So remember the a, the b, and the c, you can write it in the first notation that we learned with angle brackets. When you do it like this, you don't put the I, the J, and the K. This is called unit vector notation. This one's not. You just put the A, the B, and the C, and those would all be the components of your vector. And I can't really do it, but if you had like a light and you had a vector, what you could do to see the different components, like in 2D, let's say you had 2 walls like that, and then you had a vector like this. What you could do to see the components of that vector is imagine you had a light shining down. Well, if you shined a light down on that vector, it would make a shadow. And the shadow would be right there. That's where the shadow would be if the light was shining straight down. Now, if the light was shining to the right, this vector would block the light in this spot right here. Wherever the shadow is, those are the components of the vector. So you could do the same thing in 3D. If you had something, like this, and you shine a light towards it, you get a shadow on the board. If you could shine a light down, you'd get a shadow, if there was like a floor here, you get a shadow on the floor. And then if you shined a light, let's see, toward the board, down, and then the other axis would be, it would be shining a light this way. And you had a piece of paper right here, and you'd get a shadow. Those shadows are the components of the vector in 3D. But it's kind of hard to draw, so we're going to stay away from drawing it. What else? We talked about a vector that starts at the origin, and it has a special name. Okay, I drew various vectors, and I said you can start anywhere you want, but there is a place that's most common, and that's to start at the origin. Does anybody remember what we call a vector that starts at the origin? You had to calculate some of these on the test. Yeah?
Unit vector?
For what?
A unit vector?
So unit vector, that's a vector that's 1 unit long. The term I'm thinking of does end with vector, but not unit. Yep.
Position vector.
Position vector. Yep. So you have that exact sentence in your notes from Monday. And it's the same thing in 3D. A vector that starts at the origin is called a position vector. So now, let's remember what the formula was to find a position vector in 2D, and then we'll just make a small extension for 3D. All right, so there's how you found a position vector in 2D. Okay. And you guys did this on the test. Now, what do you think we're going to add onto that formula to make it 3D? Yeah. Okay, can you be a little more specific?
There'd be another comma, then z2 minus z1.
Yeah, there's going to be another comma, and then a z2 minus z1. Okay, so that would be for 2D. They'll give you an initial point and they'll give you a terminal point. And the initial and the terminal point will just have an x and a y in 2D. All right, so now let's extend it to 3D with what Jake just said. So now your initial and your terminal point will have an x, a y, and a z value. There's going to be a third value. So x1, y1, and z1 is the starting point. Call it P1. x2, comma y2, comma z2 is the ending point, or terminal point. Call that one P2. And to find the position vector between the 2 points, you're going to find the difference in the x's, comma, difference in the y's, comma, and now do the difference of the z's. Right? That's why I'm saying if you saw a problem in 3D and you knew how to do 2D, you probably would have been okay. Right? And that's the last thing that we did on Monday. Notice we skipped all the sketches. So this basically was Monday's lesson again, but now I did it in 3D for you, but without any sketching. Any question on the formula? Okay, let's try an example of that. So on the test, you had a couple questions that said find the position vector. The only difference was I didn't give you a z. Now you have a z. All right. So Ethan, to find, and this is why I say you should try to follow the order, even if it's not important, because this time it is important. All right. So we do have to follow that order. And can you tell me what the calculation is for the x component?
4 minus 1.
4 minus what?
-1.
Yep, 4 minus -1. And how much is that?
5.
5. That's the first part. 4 minus -1. All right. Chris, what's going to be my y-axis component? Or you know what? Just tell me the calculation first.
6 minus 2.
6 minus 2. Now, can you tell me what that is?
4.
4. So 5, 4. And Tyler, the calculation for my z-axis component.
2 minus 3.
And 2 minus 3? -1. There you go. So that is the position vector written with the angle brackets. If they wanted it as a unit vector, you could do it like this. 5 of the i's plus 4 of the j's. And what's the other unit vector that we use now in 3D besides I and j? Yep.
This will be negative 1k.
Yeah, minus 1 of the k's. You can put minus 1k or you could just put minus k. Both of those answers are the same thing. I think on the test, I asked people to do it this way. So that's what I was looking for. Question on position vector. All right. So Tuesday. So let's look at some formulas that we did on Tuesday. So Tuesday, we learned how to add, subtract, scale vectors, and find the magnitude, all without sketching. And we saw that it was really just combining like terms. So let's say we want to add 2 vectors together. If it was 2D, the way you do it is you take your x components, you add them up. You take your y components, and you add them up. If it was 2D and you wanted to subtract your x components, and subtract your y components. Now, to do this in 3D, we just have to extend that formula following the same pattern as what came before it. So, anyone think they know what's going to be the last part of our formula? Yep.
Z1 plus or minus Z2.
Yeah, plus or minus just meaning if you want to add or if you want to subtract. They just combined it all into one formula. All right, so if you want to add, you add the x's, add the y's, and the new part now is to add the z's. And that's how you would add them. This takes the place of taking a vector and another vector and putting it on the end and then drawing in the diagonal. We're not doing that. You could. It works in 3D just fine. But that's hard to do. All right. The next formula we looked at was when you multiply a vector by a number. And anybody remember what we call this number? Because it can make the vector longer, shorter, or flip it. Yep.
A scalar.
It's a scalar. And the scalar was kind of like a distributive property. If you had a 2D vector and you wanted to scale it, you multiply the x component by the scalar, the y component by the scalar, and you were done. Well, now we're going to multiply the z component by the scalar. So multiply the x, the y, and the z by whatever number you're scaling by. Right. And I think the last formula in this group that we looked at on Tuesday was this one. What does it mean when you put the double bars around a vector? Chris?
You're finding the magnitude.
You're finding the magnitude. So on Tuesday, that was the formula for the magnitude. It was the x component squared plus the y component squared, and then you take the square root. Okay, now let's make it 3D. To take the formula we had on Tuesday and make it 3D, what do you think is going to be the last thing that you put under the square root? Yep.
Plus d1 squared.
Yeah. We're going to do it one more time. Plus z1 squared. So this is how you find the length of a three-dimensional vector. Square each component, add them all up, and then take the square root. Any questions on those formulas in 3D? Let's try a couple of those. All right, so we've got two vectors, v and w. Okay, I filled in numbers for all of them. V has components of 2, 3, negative 2. And w has components of 3, negative 4, 5. And the first thing I want to do is add those vectors together. All right, so Matt, if I add those vectors up, can you tell me what my first part would be, which represents the x component?
5.
5.
I.
Yep. So you're going to travel 5 units on the x-axis. Now we're going to figure out how many units on the y. So Abigail, what would I get for my y-axis component? Yep, negative 1. And what letter goes with it? J. So we have 5i minus j. And Jack, what about my z-axis? 3k. So if you were building this vector, you'd need 5 of the i's, minus 1 of the j's, and then 3 of the k's stacked on the end of it. Okay, question on that? All right, let's do a magnitude. So let's do magnitude of v. Casey, when I usually mention this every time, when you want to find the magnitude, what's the first thing you should write down? Sorry, say it again? Did you say squared? Yeah. No, not something squared. There's gonna be something squared, but usually not the first thing you write down. Yep,
Square root.
square root. So I want to put that first. And Eli, can you tell me what's going to go under the root for my first step?
2 squared.
Yep, 2 squared. Plus, Francesca, what's going to be the next thing that goes under the root?
3 squared.
3 squared. And if this was 2D, you'd stop right there and you're done. Remember, these are like 2 sides in a triangle. Basically like this. 2, 3, and you're using the Pythagorean theorem to find the hypotenuse. Well, we're still kind of doing the Pythagorean theorem. It's just 3D. So we need one more number. Ethan, what's going to be my last thing?
3 squared.
What is it?
3.
We already got that one.
Oh.
So we did the 2 and we did the 3. What number is left?
Can you repeat what I'm supposed to be looking at? I lost.
The magnitude of V.
Negative J.
Tell me what's V? What are you looking at?
2I plus 3J minus 2K.
Yes. So we got the first two. 2 squared plus 3 squared plus...
3K.
So we did this.
Yeah.
We did this.
Yeah.
What's left?
Negative 2K.
So what do we put right there?
Negative 2.
And then what do you do to it?
Square.
Square. So negative 2 squared. So we got 2 squared, 3 squared, negative 2 squared. Just square each component, add them up and take the square root. And Chris, what will that give me?
You'll get square root of 17.
Let's see, that's going to be 4 and 4 is 8 and 9 is 17. Yep. And that's the distance in 3D, square root of 17. All right, and the last one, and then this will finish up everything we really did on Tuesday, and now we'll go over what we did yesterday. And that'll be it. 3W. So this is a scalar product. Tyler, if I take W and triple it, which would mean basically make it 3 times as long, what would be my new vector?
9 pi.
Yep.
Minus 12J.
Yep.
Plus 15K.
I need to see what it was. Yep, plus 15K. Perfect. Any question on how we got 3W? You just triple each component, just like a distributive property to each number. Times 3, times 3, times 3. All right. So now that covers everything that we really did Monday and Tuesday in 2D. Now, this is the newest thing that we learned, dot product. And now we'll do a dot product in 3D. So for this one, I'm not going to put recall and put the formula because we just did it yesterday. The other ones I put the formula because they were a little longer ago, but this one was just yesterday. So, without me saying anything, anyone think they can tell me how you would find the dot product between V and W? Eli?
Multiply the x's plus the y times the y plus d times d.
Yeah. So yesterday, multiplied the x's plus you multiplied the y's. Now you're going to extend it to be 3D. Plus, you now multiply the z's. And that's how you do a dot product in 3D. I usually like to try to get this lesson in before a test because it's kind of a good review of really everything that you did on the test. It's just all in 3D. So if this was going to be on the test, what I would have done is probably added about 5 more questions to your test. And I just would have given you 3D examples of all the stuff you did in the first part of the test. All right, so we got our formula for the dot product. And let's see if we can find the dot product between these two vectors. 2, -3, 6, and 5, 3, -1. Okay, Jake, can you tell me first 2 numbers I would multiply together?
2 and 5.
Yep, 2 times 5. And Sarah, what comes right after that? Right before that.
Plus.
Plus, yep. So the plus, then the -3 times 3. And Matt, what comes right after that?
V plus.
Yep, plus. And Abigail, the last 2 numbers?
6.
Yep, 6 and -1. All right, let's do that up, and that's our dot product. All right, so Casey, 2 times 5 gives me how much? 10. And Eli, -3 times 3?
-9.
-9. And Francesca, 6 times -1?
-6.
-6. 10 minus 9 is 1. 1 minus 6 gives you a dot product of -5. And that's doing a dot product in 3D. Now, the last thing, we did this yesterday. What did we use the dot product for? Yep.
Was it finding an angle between 2 vectors?
Yep. To find an angle between 2 vectors. Right, so let's finish up with finding an angle between 2 vectors in 3D. Does anyone remember the trig function that was on the left-hand side when we did dot product? Matt?
Cosine.
Yep, cosine. Well, it's exactly the same formula as yesterday. And if you're like, well, wait a minute, every formula we learned, we had to extend it a little bit for 3D. Well, this is extended for 3D. Each individual part of the formula has been extended. This is a 3-dimensional dot product, which is extended to 3D when you do this part. So that's how the top has been extended. This is a 3-dimensional magnitude, and that's a 3-dimensional magnitude. And both of those are extended to 3D when you do this part, when you square the z component. So the formula has been extended to 3D. The individual parts of the formula. All right, so let's finish up by finding an angle between 2 vectors. Just because we've already done a dot product, I'm going to use the same 2 vectors we just had. So we're already partway done. We already have the dot product. So the vectors were, V was 2, -3, 6. Just rename these. So V was 2, -3, 6, and W, was that 5, 3, -1? Let me check. Okay, yep. All right, so let's find the angle between those 2 vectors. Okay, first thing we need is the dot product. Can someone remind me, what did we get for the dot product? Francesca?
-5.
Okay, so we got that. Now we need to find the magnitude of V. So how about, Ethan, can you tell me, what do we usually put when we are finding a magnitude first?
Square root.
Square root. And Chris, can you tell me what would go underneath the root to find the magnitude of V?
That would be 2
2 squared minus or plus 3 squared plus negative 3 squared.
Yep.
Plus 3 squared. Plus 6 squared.
6 squared. Okay, so that's going to give me 4, 9, and 36. What's 4 plus 9 plus 36? Jack?
49.
49. So that's the square root of 49, which is 7. All right, so we've got 2 out of 3 of the things we need. We've got the dot product, we've got the first magnitude, we need the second magnitude. So magnitude of, oops, that's trying to use the same names I did in the last problem. So we're using V and W as names. All right, Tyler, can you tell me my last step to find the magnitude of W?
You take the square root of 5 squared plus 3 squared plus negative 1 squared.
Yep. That's going to give me 25 plus 9 plus 1. That's 35. Would have been nice if it was the square root of 36, but that's what it is. All right. And now let's fill in our formula and find the angle. Okay, Jake, what trig function goes on the left?
Cosine.
Cosine. And Sarah, what's going to go in the numerator?
-5.
Yep, -5. And Matt, what's going to go in the denominator?
7 square root of 35.
7 square roots of 35. And Abigail, my last step to get rid of cosine and get theta by itself.
Inverse cosine.
Yep. So we're going to take the inverse cosine of what I have on the right hand side. Be careful when you type it. You're probably going to need extra set of parentheses when you start your denominator. Just like that. Okay, I am in radians, so I'm going to switch that out so I'm in degrees. Okay, so that's how you type it in, and that's your answer. 96.93. Any questions on it? All right, so that's pretty much how we do vectors in 3D. Not really that much harder than 2D. All right, so I'm going to give you guys, you've got the rest of the time. So you got about 40 minutes. And you have 9 questions. Okay, if you get those 9 questions done, then there's no homework. If you don't, then I'll check that after break or after the shop week, and that'll be our first homework for term 4. Right, but you got a little bit of time to work on that right now.